Okay, let's dive right into this. If you've ever wondered why a computer network doesn't just, instantly collapse under the sheer weight of its own data, you are in exactly the right place. Because every single time you send an email, print a document, or even just connect a new device to a Wi-Fi network, you're generating invisible data traffic. And without the right structural rules in place, that traffic would honestly turn into absolute network chaos. Looking at the source material for today's explainer, it is fascinating to see exactly how network engineers prevent this kind of meltdown. We're going to dig into the blueprints of broadcast domains and VLAN basics to see exactly how they keep our data flowing smoothly. Here's our quick roadmap for the explainer today. First, what are broadcast domains? Second, taming traffic with VLANs. Third, extending to wireless APs. Fourth, the magic of VLAN tagging. And finally, best practices and routing.
All right, Section 1. What are broadcast domains? I want you to picture a massive, busy city intersection where the traffic lights have just completely failed. Unmanaged network traffic is exactly like that chaotic intersection. Cars are honking, everyone is trying to move at once, and nobody can actually hear the specific instructions they need. That is an unmanaged broadcast domain, which is simply the area in a network where all devices receive broadcast frames. Without structural boundaries, it's basically just a giant, really loud room. If one device shouts, saying, "Hey, where's the printer?" every single other device in that domain literally has to stop what it's doing and listen to that shout. And when hundreds of devices are shouting all at once, you get massive noise. Every single device hears every single broadcast, causing a crushing wave of traffic that bogs down performance for absolutely everyone. So how do we fix this? Well, we introduce hardware. But keep in mind, not all hardware treats this noise the same way. Unpacking the source material, it's actually really interesting to compare how routers and layer 2 switches handle these broadcasts. A router is essentially like a thick concrete wall. Routers completely break up broadcast domains. When a broadcast frame hits a router, it stops dead. Now, on the other hand, layer 2 switches simply forward broadcasts. But here is the critical part. They forward them within the same VLAN. They don't break up the domain entirely on their own, but they play a totally vital role in directing the traffic where it needs to go.
Let's move on to Section 2, taming traffic with VLANs. Basically, VLANs confine broadcasts to specific ports in the same VLAN. A layer 2 switch will absolutely not forward broadcast frames beyond the ports assigned to that specific VLAN. Think of a VLAN, which stands for Virtual Local Area Network, as a way to create dedicated traffic LANs. You're taking that one massive noisy room from earlier and putting up soundproof glass walls. The accounting team is in one VLAN, right? So their devices only hear broadcasts from other accounting devices. The engineering team is in another VLAN, hearing only their own chatter. You're confining the broadcasts, stopping the noise from flooding the entire system, and creating highly efficient, separated environments.
Section 3. Extending to wireless APs.
So we know how to physically separate traffic by plugging cables into specific switch ports, sure. But we live in a modern, mobile world. What happens when we go wireless? When the data is just flying through the air around us, how do we maintain those nice, neat, soundproof glass walls we just built?
The answer is incredibly elegant. Wireless access points, or APs, forward broadcasts strictly within the same SSID and VLAN. As the source explains, each SSID can correspond to a different VLAN to keep broadcast traffic separated. So you know when you pull out your phone and see a guest Wi-Fi and a corporate Wi-Fi broadcasting from the exact same little box on the ceiling? Those aren't just different passwords. Those SSIDs are acting as invisible boundaries right over the airwaves. Connecting to the guest SSID drops you squarely into the guest VLAN, meaning your broadcasts are completely 100% isolated from the corporate data.
Which brings us to Section 4. The magic of VLAN tagging. And this brilliantly illustrates a fun question. How does the switch actually know which invisible airwave bucket your data belongs in once it hits the physical wire? Well, it uses 802.1q, which is a protocol that tags packets with a specific VLAN ID. Imagine you're checking a bag at an airport. The airline agent slaps a barcode tag on your suitcase that tells the conveyor belt system exactly which airplane it needs to go to. That is exactly what the SSID does using 802.1q. As your data enters the network, it gets stamped with a tiny digital luggage tag, a VLAN ID, so that as it moves through the cables, the network knows exactly which dedicated traffic lane it belongs to. Looking at how this sequence builds in the source material, it's pretty straightforward. Step 1. Traffic arrives via the SSID from your wireless device. Step 2. The access point instantly tags that packet with the 802.1q protocol,
assigning its VLAN ID. Step 3, the traffic travels across a trunk port. Now, this is a vital concept here. Switch ports connected to APs are usually trunk ports. A trunk port is kind of like a massive multi-lane highway cable that allows multiple completely separated VLANs to pass over the exact same physical link at the same time. The data doesn't mix at all because of those 802.1q digital luggage tags, keeping the broadcast domains beautifully separate even while they share a single cable. And finally, Section 5, Best Practices and Routing. Straight from the source material, here is your essential checklist for success. First, plan your VLANs by user groups. Think logically about who actually needs to share a broadcast domain. Second, configure switch ports connected to APs to be trunk ports, ensuring that multi-lane highway is open and ready. Third, meticulously map your SSIDs to the right VLAN ID so your wireless users actually end up in the correct virtual rooms. And fourth, always test connectivity to confirm isolation. You absolutely have to verify that those soundproof glass walls are holding up and keeping the broadcast noise contained. But wait, that raises a really critical, logical question, doesn't it? If VLANs are completely isolated, if we've successfully trapped all the noise inside these individual glass rooms, how do they ever communicate with each other when they actually need to? Like, what if an accounting computer legitimately needs to send a file to the engineering printer? The solution here is inter-VLAN routing. To make this happen, the network uses something called switch virtual interfaces, or SVIs, on Layer 3 devices. A Layer 3 switch, or a router, acts as the intelligent bridge between these isolated rooms. It handles this by using these SVIs, with each one specifically assigned to a VLAN's IP subnet. And here's the final resolution, really the master trick of network design. The Layer 3 device actively routes traffic between those VLANs, enabling secure, targeted communication while keeping each VLAN's broadcast domain totally separate. The noise stays trapped, but the specific, necessary messages are allowed to politely walk through the door from one room to another. It's the ultimate balance of order, security, and efficiency. So the next time you connect your phone to a Wi-Fi network, I really want you to think about all the invisible architecture working behind the scenes. How are the user groups safely separated on your own home or corporate network right now? Are your smart TVs and laptops sitting in the same noisy broadcast domain, or are SVIs and VLANs actively organizing the chaos for you? It's a fascinating structural puzzle hiding right in plain sight. Thanks for checking out this explainer with me today.